momentum is kind of a funny topic because it's something that people have a really good gut feeling for what it is and how it works, but they struggle to define it. In fact, a lot of books use a definition that I absolutely hate and you should never use. Tons of both high school and college textbooks define momentum as the inertia of motion. That is a nonsense phrase. Inertia is how much mass something has and how much resistance it has to being accelerated by a force. And that number doesn't change whether something is moving or not, unless you get close to the speed of light, but don't worry about that. That number doesn't change. And so this phrase, inertia of motion, is trash. But the reason people use it is because they have a hard time coming up with a better definition. It's the goiness of an object. How hard it is to stop, no, that's still mass. How much effort it takes to stop, that's probably work. What is momentum? The thing is, momentum has a mathematical definition that is extremely clear. It is this. Momentum is mass times velocity. We can see this very easily using a cart and a block. So let's check it out.
Send in a cart, it pushes the block. Send it faster, it pushes farther. Doubling the mass of the cart also increases its momentum. Easy, right?
A change in momentum is called impulse, and impulse is represented in most textbooks as a capital J, and the textbook we use for AP, it's a capital I. Interestingly, the AP got rid of that and decided to just use delta P, which is change in momentum. So impulse is change in momentum. Do not confuse it with an impact, which is when one thing hits another. So we might talk about an impact force, but that is not the same thing as an impulse. An impact could cause an impulse, but an impact is not the same thing as impulse. Change in momentum is force times time. If you put a force on something for a certain amount of time, that is the change in momentum. It's pretty handy. 20 newtons times 2 seconds, you just change the momentum by 40 kilogram meters per second. So that's impulse. And I just hinted at something there. Momentum won't change unless there is an impulse, unless there is a force times time. And if we take Newton's laws and we say, okay, for every action there's an equal and opposite reaction, and so forces are equal and opposite, and we apply that to this idea of impulse, if I push on something in this direction for a certain amount of time, it pushes on me in this direction for the same amount of time. Whatever impulse I give it, however much I've changed its momentum, is how much it has changed my momentum. We can exchange momentum, but we can't change the total amount of momentum. What that means is that momentum is conserved. Momentum can never be created or destroyed. It can only be transferred from object to object. If we look at a closed system, the total momentum in a closed system will remain one constant number. But if you look at an open system, if some force comes from outside the system and causes an impulse, then you get something very much like the work-energy theorem. This one is called the impulse-momentum theorem. The impulse-momentum theorem is very much like the work-energy theorem. It's initial energy plus or minus work equals final energy. Well, initial momentum plus or minus impulse equals final momentum. And we can use that to solve all sorts of problems that wouldn't have been solvable prior to knowing that. When momentum is exchanged between objects, that's because they've hit each other most likely. Two things come in and hit. This is called a collision. There are two major types of collisions. An elastic collision is when two objects hit and they bounce off of each other and kinetic energy is conserved. There is no such thing as a law of conservation of kinetic energy. It just happens to be conserved in elastic collisions. Elastic collisions are actually impossible at the Newtonian level of you and me and cars and ping pong balls and things, but billiards come pretty close, bumper cars are kind of close, things like that. On the subatomic level, when you're dealing with electrons or atoms or molecules, elastic collisions are extremely common. Inelastic collisions are collisions where when things hit, they will deform, their energy will turn into the deformation of the object doing work on each other to create thermal energy and internal energy, sound, heat, things like that. So an inelastic collision is one where things hit and stick. Regions, that's all you need to know for the difference, is hit and bounce, elastic, hit and stick, that's inelastic. AP, it's a little harder because two things can hit and bounce in a way that still doesn't conserve kinetic energy. So to really prove whether or not something is inelastic or elastic, what you'd have to do is apply kinetic energy before and after, calculate it and compare it. If it's the same, then it was elastic. If it's not the same, if there was a loss or somehow a gain, then it would be inelastic. Finally, an explosion is just any time you have an object come apart, or two or more objects that are together come apart because of some kind of internal forces. This could be a literal explosion, what we think of, like chemicals, fire, etc., with a big boom, but it could be something as simple as a spring or two people on roller skates that push away from each other. Anytime you have things coming apart like that, that is an explosion. And really, it's just kind of the reverse of a perfectly elastic collision where two things come, hit, and stick. Physics doesn't really care if time flows forward or backward on any of these equations. So coming in and sticking versus starting off stuck together and then springing apart is very much the same thing. And it's exactly the same to calculate.
A few final notes. It should be obvious that in an elastic collision where carts have equal mass, they're going to exchange velocities, like this. Very massive objects aren't all that slowed down by inelastic collisions with less massive objects. And the more massive objects tend to win out in head-on collisions, which you'd know if you've ever hit a bug with your car. Elastic collisions equally favor the more massive cart, but there's a point here I want you to see. When a more massive cart hits a less massive cart, they tend to be moving in the same direction afterward. But when a less massive cart bounces off a more massive cart, it tends to reverse direction.
So there you go. That's pretty much all the concepts for this chapter. The next thing we're going to do, our next video, is just going to be sample problems, which I will divide up into regions and AP appropriate and AP only appropriate. See you there.